So now we're going to talk about the number one way that interference actually occurs, and that's through path difference. Now, path difference actually causes a phase shift. So go ahead and burn that in your head. A path difference causes a phase shift. Path difference is whenever one wave starts before or after another wave. So one has to go a further distance than the other. Now, path difference of one or more whole wavelengths gives you no phase shift, and it's going to give you constructive interference. So let me show that here on this little drawing up here. I have two waves, one in red and one in blue. So there's the red, here's the blue. And whenever there is no path difference, they both start from the exact same place. Obviously, you have constructive interference. You can see how everything lines up. What happens, though, if I start the blue wave one whole wavelength in advance? So I'm going to slide this blue wave now to where it gets a whole wavelength in advance, and then it's not exactly perfect because my drawing isn't exactly perfect. But if I slide it there, I go up, I go down, and then I'm back starting over again. A entire wavelength in advance gives me constructive interference again because it gives me a phase shift of 2 pi. And anything 2 pi, 4 pi, 6 pi, so forth, so on, actually gives me no phase shift in the end. And likewise, if I continue to slide it, right, I would continue to get, like, here's a path difference of 2 whole wavelengths, or in our terms here, in lambda, some whole number times lambda. Anytime you start a wave a whole wavelength ahead of another wave, assuming that these are identical waves, we're going to get to terms monochromatic, we're going to get to terms coherent, but assuming that one wave is starting, that there are two waves are the same, if one wave starts a whole wavelength or 2 whole wavelengths in advance of another, you're going to get constructive interference. Now, and given by the equation n times lambda, where n is any whole number. So if you have a path difference, or one starts ahead of the other, 1 wavelength, 2 wavelengths, 3 wavelengths, constructive interference. Now, destructive interference means you need half wavelengths. So for example, what if I took my blue wave and I pulled it over where it started 1/2 wavelength. So it goes up, that's only half of a wave. The blue wave is starting half a wavelength in advance, and then it comes back down. Notice those are perfectly out of phase. You're going to get destructive interference, or pi out of phase, a pi phase shift. So a path difference of half wavelengths leads to a pi phase shift, aka destructive interference. So what we can say here is destructive interference occurs at any whole number plus a half. That way we always end up with some half number right here times your wavelength. So this would be a 0 for n, right? And then if I continue to slide it over, right, there's a hole, so I got to keep sliding. Now I'm back to 1.5, right? So n would be 1 plus a half, 1.5 times the wavelength. Started 1.5 wavelengths, meaning you can see 1.5 wavelengths there in advance. Once again, I get destructive interference. So anytime you have whole wavelengths in advance, or whole wavelength path differences, you get constructive interference. Anytime you have half wavelength path differences, you get destructive interference. Now, if what I just said was very confusing to you, you might need to do 2 things. First, you might need to go back to the video on phase difference and go back over that, and back to the video over constructive and destructive interference to get that idea burned into your head. Then come back and rewatch this slide on the video to think about path difference and how that affects phase difference to give you constructive and destructive interference. Let's look at how path difference can actually occur, and then cause what we're going to say is interference patterns. So whenever light, or any wave, I'm just going to use light in this case, passes through a small opening, such as these, so I have light waves coming in that are parallel to each other, so that they're coming from a very far off source, let's say, and they pass through these slits, diffraction will end up occurring, meaning that these points will become brand new point sources that the light will radiate from. And let me actually change color, even though it's still red. I want to change color for this bottom one here. And so what's going to happen is you're actually going to start spreading out. Both of these would start causing the light, like from here, the light would start to spread out in all different directions again. And then from this spot, the light would start to spread out in all different directions again, meaning that the waves are going to end up overlapping at different spots. Now let's take a look at some of the specific distances that we could travel. What about light that comes from here and then would intersect light from this bottom one Didn't exactly draw that as a straight line, but I think we get the idea. Right there at the center, so at a spot perfectly between the two slits. If we went out perpendicular there, all the way to a screen over here on the far end, where we could see what was happening. Well, if this top one went some distance, we'll call it A for now. That means this bottom distance also traveled some distance A, they would have the exact same path difference. And what we saw on the previous slide was that if the path difference is 0, then we're going to end up having constructive interference. So the two sources, the two light sources, would end up adding, giving you a constructive spot or a bright spot there. Let's look at that again, going up to maybe another what's going to be constructive spot, right? So you end up having this other bright spot up here. Reason why for that is this top one, if this is distance A going from that top slit over there, that means the distance this bottom one has to go is A plus lambda there. However far it ends up traveling plus one wavelength. That's going to end up giving you constructive interference. So for all of these constructive interference spots here, what we can say is that you're actually increasing by one wavelength the path difference between light that would be coming out of, because of diffraction, one slit compared to the other there. So here the path difference would be 0. At the next bright spot, the path difference would be 1 wavelength. At the next bright spot, it would be 2 wavelengths. And the exact same going down, right? Because then the path difference to this bottom end too, if this distance right here was A, then the distance coming from the top one would be A plus 2 lambda. Now, if we wanted to look at destructive interference, meaning that the light completely cancels out, if we make this distance A right here, that would mean that this distance coming all the way down to that same spot would be A plus 1/2 lambda, half a wavelength further there. And then you kind of get the idea. We can actually count this up using what we talked about in the last slide. Right here is going to be 1.5 lambda path difference. Down below there will be 2.5 lambda path difference. Going up again, 0.5, 1.5. 2.5 lambda path differences. So you end up getting phase differences because of path differences, because whenever you're dealing with two-slit interference here, you actually will have one light source have to travel a shorter distance than the light from another source. Now, that idea right there of path difference actually leads to this equation whenever we're dealing with constructive interference. So let's actually delete off those two there and point it out going to with constructive interference. So we're talking about going to this spot right here to where you have A and A plus lambda going up. So S is the distance from the central order maximum to the first order maximum. Uh, Lambda is the wavelength of light that is actually coming in. D would be capital D, the distance from your slits to your screen that would actually show you the interference pattern that occurring, and then lowercase d, the distance between the slits. Now that uses the small angle approximation. You can check out the other video that's posted that's very similar to this video, just goes a little bit more into depth to where this equation kind of comes from. So let's do a simple example problem with this. This is really a plug-chug problem. Some of the more interesting ones actually are asking about wavelength, but that's also pretty straightforward whenever you recognize that constructive interference, you're going to have whole number wavelength path differences. Destructive, you're going to have half wavelength path differences. So here we have monochromatic coherent light coming in, passing through slits. The slits are 92 micrometers apart, and the first order maximum is 5.3 centimeters above the central maximum. And they give us the distance for the screen, and they ask for lambda. And so it really does just become a simple plug-chug. Manipulating my equation around for lambda, and now we can substitute numbers in. And whenever you solve that through, it turns out to be 7.5 times 10 to the negative 7th meters. Don't forget to deal with the prefixes micro times 10 to the negative 6th, centi times 10 to the negative 2 whenever you actually work out your math. If we were to put this in nanometers, nanometers times 10 to the negative 9th, this would be 750 nanometers, which is red light that we would actually have coming out.